Good afternoon. This is my second talk in the video series of the lecture, which I started with the title Graphene and Amazing Nanomaterial. For recapitulation, I want to mention some of the points which I covered in my first lecture. I discussed what exactly is nanomaterial, what is its measure, why it is so important in the technology and industry. And also, I talked about how these nanomaterial properties, they behave fantastically different from their counterpart bulk materials. So these things I tried to cover up in my first lecture. Today, in this lecture, to continue, first of all, I will try to say that what exactly is the boundary line between the bulk material and the nanomaterial. See, I told you that the nanomaterial, they are of the order of the size 10 to the power minus 9 meters. But we should not think that the entire material in all the directions, I mean the x direction, y direction, z direction, in three-dimensional figure, they must be of the order of 10 to the power minus 9 meter, and then only they will exhibit the nanomaterial properties. No, that is not correct. If we take if we take a bulk material, the large size in x direction, y direction, z direction, but if we just size it to the nanometric size in only one direction, say I am taking a three-dimensional body, finite dimensions, say micron, 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 or centimeter, centimeter, centimeter. All these three directions are large direction, large size. But now if I just size it, say this is my x direction, this is my y direction, and this is z direction. Now gradually, I scale down the z direction. Then it will come to a flat plate like this. One dimension is becoming of the size nano, this distance. This is a very short distance. It is of the nano. Yes, this will differ in its property from this counterpart bulk. So this, what I mean, that there is no scope to think that all the directions must be very low size. No, not that. So with this very simple idea, let me tell you that how much is the nanometric size to show the nanometer, the nano property of the material. Is it 1 nanometer? Is it 2 nanometer? Is it 500 nanometer? The answer is again simple, that some material say I am taking copper. It will show its nano property up to say 70 nanometer. For example, this is not a correct figure. For example, so if you come down from 70, then yes, it is a nanometric substance. It will show a fantastic behavior from the bulk copper. But say zinc, if you take zinc, say it is 91 nanometers, suppose. Then it can show from 0 to 91 nanometer, it can exhibit the peculiar property, which is different from its bulk counterpart. So, what exactly is the nano size? There is no clear-cut answer. There is a controversy. But people that take for granted that up to 100 nanometer, we can define a material as a nanomaterial. So, this is the standard size of the nanometric material. Okay. Now, with this idea, let me divide what are the different types of nanomaterials. See, I have started from a bulk X direction, Y direction, Z direction. Now look here. That the free electrons, these electrons, if you take the semiconductor or use a metal, there are so many free electrons are here. In the semiconductor, there are free electrons in the conduction band. So, we are taking interest on the free electrons, and these free electrons, if the size is very big, then the electrons can move both in X direction, Y direction and Z direction freely. So, an electron can move in any direction. This R vector, R direction, this direction and so on. So, this, it can have the degree of freedom 3. I mean, it can move in 3 directions quite independently. Fine. Now, if the size is gradually shrinking, I am now pressing from the top, and I am pressing this one, and it is coming to a size like this. It looks like a plate. Looks like a plate. Let's see, for example, I will show you. So this is the bulk material. This is the bulk material, the X direction, Y direction and Z direction. It has some property, say copper or zinc or anything like that. Now, what I do is this, gradually I am sizing, right? I am scaling down and down. So, the top comes to the bottom, almost it mixes with this, and it now looks like thin plate. This looks like this. See, the thickness is extremely small, not 0, but it is of a nanometer size. But I told you that within 100 nanometers. Of course, it depends upon the material that I have already told you. Its property will drastically change, though the same material. Okay, now here, why it will change, you see, that I shower it by light. I disturb it by electricity. I disturb it by magnet, and so on and so forth. Its property to thermal disturbance, to magnetic disturbance, to electrical disturbance, to optical, light disturbance, it will show its different characteristic features. The same optical feature here, the same material, the feature will be changed. For example, suppose it absorbs, suppose yellow light. Yellow light will not be absorbed here, but the same material. For example, so we shall see why it is like that. See, every reaction, the physical reaction, depends upon the energy of the electron which is inside here. Now, electrons are moving with energy. The free electrons are moving here with energy in all the directions. Now, this is in scientific language, I must say that the energy structuring of the electron here and the energy structuring of the electron here drastically different. Material remains same. So, the structure of the energy, how the energy is structured means, the electrons are distributed in the energy levels. Suppose there are different energy levels, say so many electron volts, so many electron volt, and so on. The electrons are distributed in the different energy levels. The difference between the two adjacent energy levels is something here. But when you just take the sizing, the nano size, like a plate, then you see that the distance will change, number one. The adjacent interval between the two levels, it will change. And also, the number of electrons in the particular level will change. How many electrons here? Suppose it is number say 100. But if you come here, it will be changing. So, the electron distribution in the different energy levels will change. Obviously, if some disturbance is coming in the bulk material, and if the same disturbance is coming here because energy levels are changing, and electron is distributed in different fashion, which I shall discuss elaborately. Naturally, this will react with the environment, with the disturbances in a different way. So that is the basic thing. That is the basic thing, that the restructuring of the electron energies and obviously the mechanism of the reaction with the outer environment disturbance factor that will change. And this will give new effects, new physical, chemical properties. Now here you see that the electron here in the bulk material, there are 3 degrees of freedom. They can freely move in 3 directions. But here it cannot move in the Z direction because Z direction is extremely small. So it cannot move so easily. So the movement in the Z direction is restricted, and only it can move freely in the X direction, which is very long. It is not nanometer, it may be micrometer, centimeter, like that. And also in the Y direction, it is also more than nanometer. So nanometric effect will not in the X direction, not in the Y direction. So the physical property or any property that will be changing only because of the Z direction restricted motion. So in this direction, if electron wants to give some response to the outer environment, that response will be drastically different as compared with the bulk material. This is one type of structure. The structure is one direction is restricted, two directions are free. So this is my first. So it is one-dimensional nanomaterial in which the nano dimension is only one. This is the nano dimension. And freely transport, the electron can freely move, transport can move in two directions. That means degree of freedom is 2. Similarly, if now another, say I am taking y direction, which is very big, it is now coming very, very low value, this y direction. So it looks like, see, this is x, y, z. I am taking this as see only x direction. This is long. Y direction is very restricted, and z direction is also restricted, this height. So you see that both the z direction, the electron in the z direction, that movement is restricted. The electron which is moving in the y direction, that is also restricted. And electron can move very freely, only one degree of freedom, that is in the x direction. And this is your, like a well. This is called well, is a quantum well. I will explain why it is called quantum. It is a quantum well structure. So the quantum well structure means degrees of freedom is 2. It is like a plate, ultra thin plate, ultra thin film. And here it is quantum well. So the well is two-dimensional motion free. Here only one-dimensional motion is free. So the motion is restricted in the z direction, and the motion is restricted also in the y direction. Obviously, the energy structure again like this, the energy structure in the y direction, the energy structure in the z direction, that structure will be drastically changed as compared from the power. So again, restructuring of the energy levels in the quantum well, which is different from quantum well, which is different from the bond. Obviously, it will show very, very interesting property again due to its nanometric size, the quantum well. And it is used in industry, it is used in electronics, in different sectors. Now see again. So the degrees of freedom only one. So gradually the freedom of motion is restricted. The electron can move freely in the x direction only. Well, now we restrict x also. Very interesting. So cut down, cut down, cut down, extremely small piece. So it looks like this. I mean, see, all the x direction, y direction, z direction, this cuboid, the cube, this is nanometers. So electron cannot move freely, neither in the x direction, nor in the y direction, nor in the z direction. So restructuring of energy, it is in the x direction as well. Not only in the y direction, not only in z direction, it is also restricted in the x direction. This is the structure, another type of structure of the nanomaterial, and this is called quantum dot. So these are the 3 types of nanomaterials. So in 2D nanomaterial, the nano dimension is in 2 directions, the dimension is in 2 directions. and one direction, free, and that's the quantum wave and quantum dot. All the three directions are restricted. So the nano dimension, all the three dimensions are in nano order, and there is no free transport. The free transport direction is zero. The electron is completely restricted in motion, and you see that it is just like a natural atom. See, in a natural atom, the electrons are there, but the electrons cannot go out from the clutch of the nucleus. The electrons are bound here, right? So, its motion is restricted. It cannot go in X, Y, Z. It is in the influence of the nucleus. So, it's an atom, and here, this atom, which we are making here in the laboratory, and this is your artificial atom. Say, quantum dot can be used as an atom, as an artificial atom. So you see, the natural atom, and this is my artificial atom, and quantum dot, it is extremely useful in electronic industry, and very, very many applications are there of the quantum dots, which we shall see gradually. Okay.